mechanism at the fastest rate. And all we are looking at in this case, the substrates, are whether they are primary, secondary, tertiary. So that is really the critical. This is primary. Okay. This is secondary. This is also secondary. But this is actually a little more hindered secondary. And this is tertiary. And so that's what is determining the SN2 mechanism. Obviously goes through primary or methyl the best. So this is the least hindered, and therefore that would be the answer. The B is also the same set of compounds, except that now there we're asking about SN1 mechanism. So the SN1 goes to carbon-cation formation, and therefore the most stable one would be the tertiary. So this is the answer. Identify the mechanism most responsible for the major product flow reaction. And any of these type of problems, you look at the substrate, again this particular carbon, which is in this case secondary, and then look at the nucleophile or solvent or the base. In this case, it's a good nucleophile and a good base. But because this is secondary, the base character is more important in this particular case. It would have been, if it was primary, then it would act as a nucleophile. But as soon as it's secondary, then there is, the base character is particularly important, and that is going to undergo elimination by E2 process. So this is the answer. Okay, question D asks which reaction takes place as the fastest rate. And again, we need to examine the substrate, the nucleophile, as well as the solvent. Now, all the solvents essentially are same here. Temperature is same, and the nucleophile is the same. Right? So now we look at the leaving group ability and look also at the product in this case. So because SH minus is a good nucleophile and a poor base, so it is more likely to undergo nucleophilic substitution and typically SN2 reaction. So when it's undergoing SN2 reaction, we see that there are two of them that are really elimination products. So we can rule them out. Of the other two, the only difference is they are both primary carbon, but bromine versus chlorine. And bromine is a better leaving group. As we know, the halogens typically, iodine is the best, followed by bromine, then chlorine, and fluorine is the worst. So in this case, therefore, this is the reaction that's going on. Okay, question 2 asks you to consider two pairs of the following pairs of reaction, and we compare them to see which reaction will proceed at a faster rate. So the reactions are the same, the products are the same. The only difference in this case is the solvent, which is EMSO versus methanol. And if we identify this reaction, because it's SN2, it's a secondary carbon, good leaving group, and a good nucleophile. So it is going to undergo SN2 reaction. And because SN2 is particularly good in polar aprotic solvent, this reaction will be faster with EMSO than methanol, which is a protic solvent. So A is the answer. Sorry, A is the answer. This one is the answer. So the question B is, again, we're comparing in this case, and what you see is that the nucleophile is the same. The products are essentially a substitution product. The only difference is both of them are primary. This is primary, and this is a hindered primary. Hindered because the next carbon is hindered. Hindered primary. And that makes the difference between the two because it's an SN2 process. Again, this one would be better. Okay, question 3 asks you on the following 3 chlorides, start with a structure that will undergo solvolysis in methanol most rapidly. The term solvolysis means that the reaction is occurring with the solvent. And typically the solvolysis reactions involve, in most cases, not in all cases, like SN1 process. So in SN1 process, the carbocation is generated, and therefore we look at the carbon to which the leaving group is attached. So this is tertiary. This one is secondary, and this one is primary. Okay. So based on that, we know the tertiary will form the carbocation fastest, and therefore that will undergo solvolysis. Question 4, give the mechanistic symbols SN1, SN2, etc. that are most consistent with each of the following statements. Okay, so the first statement is unhindered primary halides react with sodium ethoxide and ethanol mainly by this mechanism. We know that that is typically SN2, unhindered primary. So SN2. 3-chloropentane reacts with sodium ethoxide and ethanol mainly by this mechanism. Now, all we did is change the substrate with 3-chloropentane is the secondary carbon to which the chlorine is attached, and therefore that is going to undergo elimination by E2 process. These reaction mechanisms represent concerted processes. So in other words, bond breaking and bond making takes place simultaneously. We know that's typically happening in SN2 and E2. Reaction proceeding by these mechanisms are stereospecific. Again, the stereospecificity is usually occurs in SN2 and E2 processes. These reaction mechanisms are likely to be involved when the products are found to have different carbon skeleton than the substrate. So different carbon skeleton happens when carbocation rearrangement happens, and therefore formation of the carbocation is the first step, and therefore this is likely to undergo SN1 and E1 process. And the fifth question is really drawing the different products that is being formed in this process. And again, we need to recognize what kind of reaction they are undergo, and then we can predict the product easily. So this is again a typical example of the solvolysis reaction, where the solvent is either the nucleophile or as a base it would react. And so the first step is formation of the carbocation from this bromide, which then undergoes reaction with the solvent. And because it's not a particularly hindered solvent, if you have a tertiary butanol, that will undergo more E1 process. In this case, it's the SN1 is the major product. So what we expect to see is after the formation of the carbocation, it is going to form mainly the SN1 product. But if you wish to write the E1 product, that's also fine. The major E1 product would be the double bond here. So this would be the major, followed by a minor elimination product, which would be so this is minor. The second question is, again, showing a secondary carbon here, where the leaving group is attached. Cyanide is a good nucleophile. Therefore, this is going to undergo, even though it's a secondary carbon, is an SN2 process. So in SN2, we know it undergoes quantitative inversion of configuration. Therefore, we can draw the product as this. This one is unaffected. And this one would be dash Cn. Or if you write in chair form, because the relationship is trans, this would be diequatorial. The next reaction, the same substrate, but we change the nucleophile from cyanide to ethoxide. And ethoxide will undergo, as we mentioned before, it would act as a base in this case, because it's a secondary carbon. So it's going to undergo elimination by E2. So it's going to form a double bond. This one would be unaffected. The next one is the application of the OTS, or the toluene sulfonyl group, as a living group. So we start with an alcohol treated with paratoluene sulfonyl chloride, and that converts this to OTS. And this is a very well accepted abbreviation. The stereochemistry is unchanged because nothing happened on the chiral carbon here. And so it's OTS, paratoluene sulfonyl chloride, is converted to this. And then next step, it is going to undergo an SN2 process, where the cyanide is going to attack from the other side. And therefore, we'll get an inversion of configuration, where the cyanide would come from this side, and the living group OTS will leave. So this would be the product. And stereospecific. Only this product will be formed. The next one is also SN2 reaction. The chlorine is the living group, even though this one is a secondary carbon. So S minus, which is a better nucleophile than the O minus, and a poorer base. That's why it undergoes this reaction. The T-butyl group here. And it's going to be axial. So again, it's a stereospecific reaction because it's SN2. The next one is kind of a trick question in the sense that even though you use excess sodium azide, it can only react with this carbon, which is tetrahedral, and this is primary. So the E2 reaction will, SN2 reaction will happen on this carbon. Even though you have a lot more of the azide present, it's not going to react here. This is an sp2 carbon. So all the discussion that we had so far relates to sp3 hybridized carbon. And that's why the product is very specific. It's going to only form CH2, CH2, N3. This is the only product. Yes.
So the only bases of sp2 that we would need to worry about are the ketones and aldehydes?
The aldehydes are also sp2, but they undergo different reaction than the one in here. Okay, they undergo different types of reaction. So now these two are from chapter 17. So the first one is formation of the ene, typically on the aldehyde carbonyl group. And essentially we already discovered the product really undergoes with elimination of water That's nitrogen and carbon are joined with two double bonds. Two double bonds. The rest of the molecule remains unaffected. So what we expect to see is the imine, which is nitrogen, and then OCH3 remains inside. So this is the product. And you also know the mechanism of how that really forms. Essentially, the nitrogen lone pair attacks the carbonyl group, and it is going to form so this is the intermediate that is formed, and it has a positively charged nitrogen and a negatively charged oxygen. So there are two molecules of water and oxonium ion is going to react with that. H. So this picks up the proton, and another molecule of water. There are actually two sequential states, but you can write it in one place, where it's going to generate. I'm not writing the other groups, but showing you that this is forming the OH. So then the lone pair of electron on the nitrogen can go, and it can undergo protonation, followed by elimination of this group, and then subsequent steps, you know, pretty much proton transfer and so forth, ultimately giving you the carbon nitrogen couple, right? So, etc. The next one is actually a reverse reaction of forming an acetal. This is an acetal. And the acetals can be hydrolyzed in cases using aqueous acid. So that's why the water is an important component of that. In the presence of an acid, this will be hydrolyzed. And to recognize the acetal, what you need to do, and something that I'll show you again, is actually point out the carbon. That is the carbon that was originally a carbonyl group. So you can hydrolyze that pretty easily. Make sure that you write everything else the way they are. And this is the carbon we're talking about. This one also has a hydrogen, right? So because it shows 3 bonds, therefore it has a hydrogen. So the hydrogen is intact, and now you hydrolyze them, becomes CO. And this one would be the glycol, the ethylene glycol. You don't need to show this, but this is the major product in hydrolysis that is formed. So the next one, actually, I'll do it later. This is actually kind of similar, but we'll do it later. Go through question 7. Select the combination of alkyl bromide and potassium alkoxide that would be the most effective in the synthesis of the following ethers. And so the ethers really means an oxygen is connected to 2 different groups, 2 different alkyl groups. And it's important to recognize whether they are primary or secondary or tertiary. Okay. Because we can do it in 2 different ways, and we'll see what happens with that. If we break the bond here, one possibility would be that you use the you use the bromide here on this carbon plus the alkoxide is this, right? And second possibility would be that you break the bond between oxygen and this methyl carbon. So in that case, this would be the alkoxide minus Na plus methyl bromide. And when we examine these two reactions, we recognize that this reaction will go very well. It's attacking what's important is that this carbon is methyl. It's better than bromine in terms of the SN2 process, whereas this carbon is secondary. Okay. So in this case, we are not going to get a lot of this product. Most of the product would be, because we use alkoxide, would be elimination product. So this is unacceptable method of making this. It's not going to give you very much of this product. Okay? So this is the path that you should do. And the same argument here. You can break the bond between the carbon and oxygen in the p-butyl group or the methyl group. And ideally, the methyl bromide would be the better one to be attacked. So what we want is CH3, 3, CO minus, Na plus. Oh, potassium hydroxide. Sorry, why am I writing sodium? They should all be K. Plus methyl bromide. Okay. So that will be the one. I didn't write the other one because that, again, will have the same argument that that is going to undergo elimination. Okay. Okay, describe the conversion of 1-methyl-cyclopentanol, which is shown here, to cis-2-methyl-cyclopentyl acetate. So in this type of problem, it's better to start from the end and kind of step by step you can go back to the original product or original compound. So what would I need to make this compound? Ideally, because you are attaching an acetate, you want a good leaving group here, but with an opposite stereochemistry. So if we draw that, then we use the dash, and let's say that ideally a good leaving group like etosylate or bromide, any of these. So OTS, this one we can use the acetate, CH3CO O minus Na plus, for example. That is going to undergo an SN2 process and give you stereoisomer, specific stereoisomers, such as this one. All right? So now, how do I make that? Again, we cannot make this directly from this one. But if we had a double bond here, then we can make that. So the double bond is the intermediate, as we can see, that if we use like because it's a tertiary carbon, we can carry out an elimination with sulfuric acid and introduce the double bond. The double bond can then be converted to an OH group. And ideally, we want to introduce the OH group here. If we do acid water, that's going to introduce the OH group here. So we don't want that. Ideal method would be the hydroboration reduction. So if we do hydroboration, so one is B2H6 in diglyme, and 2 is H2O2 with a base. Then we attach actually the OH group, and in the anti-Markovnikov manner, also the OH and the H would be same, right? So if we draw the product of this, because I ran out of space, let me write it here. Okay, so So the hydrogen, remember the hydrogen and the OH should be on the same side. So H and the OH. And therefore, there is another hydrogen here and the methyl group here. So this is what we will get from the diboron reaction, diboron formed by hydrogen peroxide and OH. And that is actually perfect what we want, because this OH can be converted to the tosylate. So we use the tosyl chloride to make the tosylate, and then we carry on the rest. Is this clear? So it involves, first step is making the double bond. Second step is the diboron reaction, diboron followed by hydrogen peroxide and base, to introduce the OH in the anti-Markovnikov manner. Then we convert the OH to the OTS, which becomes a good living group, and then we use acetate to kick out the OTS by SN2. All right, the second problem is not very different from the first one. Again, in this case, we want the relationship of this methyl group and the N3 as, because this is equatorial, this is axial, there would be cis relationship. Right? So the cis relationship, again, we can do it by introducing the OH by B2H6, diglyne, H2O2, and OH minus. That is going to introduce the H and the OH from the same side. So this is what is going to be formed. And now we convert this, and now again we can see that the relationship between the methyl and the OH is trans in this case. So we can rewrite this in the chair form like a diequatorial conformer. CH3 and OH. Now the OH can be converted to OTS, again tosyl chloride. So it's OTS and methyl. And now we can heat it with N3 minus and SN2 reaction. That is going to get the final product. It's okay, right? Okay. The last question asks you to circle the most polar protic solvent. And methanol is a protic solvent, it's quite polar. Ethanol is also protic solvent, quite polar. But water is the protic most polar solvent. This is the answer. These are aprotic solvent. Dimethyl sulfoxide is the most polar aprotic solvent. In this case, of course, it's unrelated, but if you ask a question about the most polar aprotic solvent, this is the best one here. These are also good polar aprotic solvent, DMF and acetonitrile. Hexane is an extremely non-polar aprotic solvent. Okay, and I picked a couple of problems from chapter 17. Go over that. Okay, this is 1734, which is asking you, these are all kind of related, that they are forming, if you have gone through the formation of the hemiacetal and acetal from a carbonyl group, it should become clear. That's really what these are all about. The first one is telling you it's a reaction of benzaldehyde with 1,2-octane diol in benzene, containing a small amount of paratoluene sulfonic acid. It's almost equal amount of two products, and they have the same molecular formula. So let's examine what really is happening. You have benzaldehyde, which is CHO. And you use a 1,2-octane diol. So let's write 8 carbon. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is the 1 and 2 OH. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So this is what they are telling you, that if you react this with a little bit of paratoluene sulfonic acid, so it's really what they are providing, a small amount of acid, and you get two products. So now the product that would be generated, you would expect that they would be acetals, right? And because it's an intramolecular compound, this OH group, one of the OH group first will react with the carbonyl, and then the other OH group will also be going to react, forming what we normally say is that these are the two oxygens, right? And so they are separated by 2 carbons. Okay. Now, one of the carbon contains this other chain of 1, 2, 3, 4, 5, 6 carbon. Okay. So this is what is formed. Now, when we examine this, we can see that this carbon is really chiral, right? Because it is connected to 4 different groups: a phenyl group, a hydrogen. This OCH2 is very different from this OCH2, which is this linker. Okay. Therefore, they are actually chiral, and therefore you would expect 2 different stereoisomers to be formed from that. And you can rewrite this structure. This is the molecular formula, which will be consistent with this, but then you can write in OH and dash the 2 different groups, how they will be attached. Right? So 2 stereoisomers. And that's why you get that. All right, the next problem asking you to actually come up with the carbonyl compound, which is really converted to this. These are compound that has both the carbonyl and the alcohol functionality in the same molecule. That's why they cyclize this way and form either hemiacetal or acetal. And as you can see, because you have OHs here, these 2 are hemiacetals. And these 2 are, because you don't have any OH, these 2 are acetals. And the real trick is to actually recognize which carbon was a carbonyl group before. So when you look at them, look at carefully the carbon that is attached to 2 oxygens. Okay. Here, this is the carbon that is joined with 2 oxygens. In this case, this is the carbon joined with 2 oxygens. Right? And likewise, in this case, this is the carbon connected with 2 other oxygens. And here, this is the carbon. So you need to recognize that first. Once you have done that, it's a very simple problem. Then we can see that in this case, really form the carbonyl. So we can actually follow through that mechanism. So you have this, then you open up the link here. That would give you the ultimately this will become the carbonyl and this will become OH. Right? The same thing here. You rewrite